In this video, I will explain you different charge distribution. These are point charge. Anyway, that's not a charge distribution. These are charge distributions. Linear charge distributions, surface charge distribution, volumetric charge distribution. Okay. Now we will also see what is the electric field intensity due to this kind of distribution and direction of field line. So first thing is point charge. So we know when we have a positive charge and a negative charge, field lines will be starting from positive and terminating on negative. So direction. This is the direction of field line. Now linear charge distribution means we are taking a conductor wire having a small diameter and we are giving a total charge of Q. Now we know that this is a conductor, right? So that will allow charges to move across. Now how will the charge be distributed? So these charges, so when I am loading all the charges here, positive charges here, this will be repelled and that will be distributed across the conductor in this way. So this will be uniformly distributed. So the whole Q is distributed over a length of L. Now we defined a particular quantity called as linear charge density. So lambda, linear charge density, that is equal to Q by L. So the total charge distributed divided by length of the conductor is the linear charge distribution. Now what will be the direction of electric field around this? Now say for example, we are considering that these positive charges are giving electric field in this direction and this is giving electric field in this direction. If this is giving electric field is in this direction, then we are violating the rule we have just learned, that electric field lines will not intersect. See, here in this case these are intersecting, so this is not allowed. So what is the possible case of electric field lines? So electric field lines will be in a way that they will never intersect. So it will be parallelly outward. Whatever the distance they go, they won't intersect. Not only in one direction, three-dimensional. So this can be simply represented as, we have a charge here, see, three-dimensionally outward. Here we have a charge three-dimensionally outward. It's three-dimensional, okay. So this one, if this one is the distribution, then this is the representation, okay. See, radially outward. Will this intersect with this? No. See, radially outward. Similarly, we have above and below. Okay, so this can be represented as bristles in a bottle brush. You have seen bottle brush, right? So the bristles, how it will be? Bristles will be in this way. One. In a brush, bristles, right? Okay, so that is that is how the field lines will be there in a linear charge distribution. Now what is surface charge distribution? We have a metallic conductor, metallic sheet. We are providing a total charge of Q. So when we are keeping it on the surface, that will be distributed across the area. So Q has now been distributed across the area. Now we define a quantity called as sigma. What is that? Here in this case, linear charge density. So what will be this? Surface charge density. So that is charge per unit area. So this charges will be in this way. So in the same explanation I have given in the previous case, here also field lines have to be in a way that they will never intersect. So how will that be? It will be in this way, radially outward in a way that they will never intersect. So for example, if this is the sheet, field lines will be in this direction. See, we have a sheet in this way, so that will be outward. We got the direction for surface charge distribution and linear charge distribution. Now what is volumetric distribution? Now let's say we have two metallic sphere. One is sorry, one is metallic and other one is insulator. Okay, dielectric sphere. If it is metallic, though inside, if it is not hollow, if it is solid sphere, still whatever the charges we are giving at the inner point, that will be directed outward, that will go outward. Why? Conductor allow charges to move, so that will simply go outward, and in outer position it will be residing on the surface. So that will simply become surface charge distribution. What is the total area? 4 pi r square. So Q divided by 4 pi r square will be the surface charge density here in this case. But if this is an insulator, whatever charges we are giving inside, that won't go outside. It cannot move, right? Insulator basically doesn't allow charges to move. So with an insulator, if you are giving a charge, that will reside itself in the total volume, that will be there. Okay, so here charge is distributed across volume, and this is represented as rho. What is rho? Volumetric charge distribution. So here in this case, surface charge distribution, if this is the case, now volumetric charge distribution, positive inside, that will be radially outward in a way that electric field lines will never intersect. So these are very important. So these concepts we will be using in coming lectures. In a linear charge distribution, in this way, like a bristles in a bottle brush. Surface charge distribution parallel, here also radially outward, so that this will not intersect each other. Okay, thank you.